So welcome to lecture number 2 on September 2nd, Math 211. And I'm gonna share my screen. And let's scroll down to where we left off. We did sample space. I don't think we did this, did we? I think the last thing we did was sample space, right? Did we even finish this problem?
Yeah, we finished that. We're on page 11, the probability distribution.
Okay, wonderful. All right, probability distribution. So just like the word distribution signifies how something is distributed, what a probability distribution describes are all of the possible numerical outcomes of a random situation and associated each one with the probability that that outcome actually occurs. Now, the key here is it has to be numerical outcomes. So if we go back to the previous slide, we see that these H's and these T's as outcomes don't work. You can't use H's and T's for this type of problem that we want to do. So what do I do if I want numerical outcomes of a random situation? I have to kind of readjust what my question is. So if I'm interested in the actual outcomes, heads and tails, then I'm curious about H's and T's. But if I say, how many heads do I get? Then that becomes numerical. Because if I flip 2 coins, then what are the possibilities for how many heads that I get? I can get no heads if they're both tails. I can get 1 heads, right? If one's heads and 1 tails, or I can get both heads, correct? So a probability distribution for that situation would be 0, 1, 2, because those are the only 3 possibilities for how many heads I can get when I flip 2 coins. Do you agree?
Yes.
Now, are these equally likely outcomes is the question. Would I assign a probability of 1 over 3, 1 over 3, and 1 over 3 to each? Or is it something different?
So according to the page before, if we look at it, page 10, there's the HH, heads, 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 tails, tails, heads, tails, tails. So there's a 25% chance of getting 2 heads, a 25% chance of getting 2 tails, and a 50% chance of getting 1 head.
That's wonderful. Do I have to elaborate on that, or did that all make sense? So heads 25% because it's 1 in 4. I mean, 0 heads is 1 in 4. For 1 head, there's actually 2 ways of getting it. So it's 50%, 2 out of 4. And 2 heads, there's only 1 way of getting that, so 1 out of 4. Of course, they do have to add up to what number? When I add up all percents of all possible outcomes, what do they have to add up to?
100.
It's got to be 100%, because it's got to be one of the outcomes. So if you ever don't add up to 100% in this kind of situation, you know you did something wrong. Does that make sense? Any elaboration required? Because that was really just excellent. Okay, so Maya, who's auditing the class there?
It's my shidduch.
Mazel tov.
Yeah, he's from out of town visiting, so.
Very nice. Mazel tov. It's very, very nice to hear. All right. Okay, so let's move on now to the next. Oh, can I hit clear? Hey, that worked. Okay, so let's scroll down. So here's another one. Write a sample space with equally likely outcomes, equally likely for flipping a penny 3 times. So remember what a sample space is. A sample space is a collection of each possible outcome. But in this particular example, it has to be equally likely outcomes. So if I do 0 heads, 1 heads, 2 heads, and 3 heads, that is a perfectly valid sample space, but unfortunately, it's not one associated with equally likely outcomes. So I want one with equally likely outcomes. Who here would like to venture a guess as to a sample space for this problem where the outcomes are equally likely.
Head, head, head.
Okay, so one possibility is heads, heads, heads. Okay. Another outcome,
Heads, heads, tails,
heads, heads, tails,
head, tail, tail.
heads, tails, tails. Before we
No.
keep going, how many outcomes are there going to be?
3.
So
Or
there's no other possibility?
no, there's many more.
So the question is, how many are we going to have? I mean, we can start listing them, but if we don't know how many we expect to have, we'll never really know whether we have them all. So how many outcomes do we expect to have if you flip 3 pennies?
6.
Okay, so 6 is a good guess. It's not correct, but it's a good guess. And let's think about it. The first flip, the second flip, the third flip. How many outcomes are there for the first flip? All right, my first coin that I flip, how many outcomes are there for the first flip alone?
1.
2.
2. It could be heads or tails, right? Right? Heads or tails, correct? Second flip, how many outcomes are there?
2.
2, heads or tails. Third flip, how many outcomes are there?
2.
Heads or tails. Now, when you got 6, it's because you added them. But what should you have done?
Multiple.
Multiplied. Because for each of these 2 outcomes, we have 2 outcomes here for a total of 4 outcomes, which we've already listed those 4 outcomes, H, 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 T, T, H, and T, T. And for each of those 4, the next one could be heads or tails. So each of these 4 go with heads, and each of these 4 go with tails for a total of 8 total outcomes. Does that make sense?
Yeah.
Yeah, so we multiply. When you have a sequence of steps and you're counting how many possibilities, by the way, this is called the fundamental principle of counting. There's a branch of mathematics called combinatorics, the mathematics of counting. It doesn't mean that you just count 1, 2, 3, and so on and consider it a branch of math. That's pretty easy. And any 3-year-old can do that up to a certain point. But if I say, how many ways can 26 people sit at 14 different tables where no man sits next to this person and that and this and that, you're giving all these conditions and all these ways. You don't want to brute force it. You don't want to have to say, well, this is a possibility and that's a possibility and that's a possibility, because there could be hundreds or thousands or millions of ways something can be done. So you're looking for ways of counting things without actually having to brute force it. In this case, 2 times 2 times 2 gives us 8. Let's actually list the 8. We have H, 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 T, H, T, T. What else is there?
T, T, T.
T, T, T. We haven't listed that one yet. Okay, what else we got?
HTH.
H, T, H. That's a new one. What else we got?
T, T, H.
Sorry, I didn't hear that.
T, T, H.
T, T, H. What else we got? That's 6 so far. So there should be
EHT.
THT. And
THH.
THH. So this is my equally likely sample space. I'll put it in braces because it's a collection of objects, and we usually denote a sample space S. It's the collection of those 8 elements, put a comma here. And now we want a probability distribution. So what we want to do is we want to list every possible numerical outcome, X. And then in this column, we're going to list the probability of getting that numerical outcome, P of X. But it has to be numerical, so I can't list any of these. And what are we after? We're after the number of heads. That's the goal of this problem. So what are all the possible numbers of heads that I can get when I flip 3 coins?
Does 0 count?
Sure, I can get no heads.
1,
I can get one head.
2,
I can get two heads.
and 3.
And three. I can get three heads. There's no way of getting four heads when you flip three coins, right? Not the way coins work. So now the question is, when we have all of the possible outcomes, now we want to list all the possible probabilities that go with those outcomes. So what is the probability of getting 0 heads when you flip 3 fair coins?
1.
100%, you mean? You're guaranteed to get 0 heads?
1A.
1/8. Remember the formula which we had last time? Let's find it here. For the probability of equally likely outcomes, you count the number of ways of getting what you want divided by the number of ways of having an outcome in general, the sample space size. So in this particular case, there's one way of getting 0 heads, but there's 8 possible outcomes, right? Hopefully, yes. How about 1? What's the probability of getting 1 head in this scenario?
3/8.
3/8. And how about getting 2 heads in this scenario?
3/8.
3/8. And how about getting 3 heads in this scenario?
1A.
1/8. And just to check that we did it correct, what do these 4 numbers add up to?
8. 8.
8/8, which is equal to
1.
1 or 100%, right? So 1 is 100%. So they do add up to the correct number as expected. Does that make sense? And can I erase everything I wrote?
Yes.
Number 1, how did you get the 3/8?
Well, look at the 8 outcomes. How many of them have exactly 1 head?
Oh,
This one here, 1,
yeah.
2, 3. So
Oh,
of the 8 equally likely outcomes, 3 of them lands with 1 head.
got it.
And similarly for the others. Make sense?
Yeah.
Okay, can I erase?
Yes.
Okay, we have a question. Why is it for 2 heads, it's not 4/8? So let's undo what I just erased. So she goes, or he goes, or she goes, why is it 2 heads, not 4/8? Well, let's take a look. How many ways can I have 2 heads? Let's change the color. How do you change color? Anyone know how to change color here?
Yeah, there's a little square.
If you click on the format, there's a square that has like a color on it.
Format.
Yeah, do you see it on the annotated?
They counted wrong.
Hold on. No, wait, never mind. I kind of wrong. She answered her own question, but I don't see a word format. Oh, here it is. I see it. I'm sorry.
Okay,
Okay,
yeah.
thank you. Thank you. Okay. So, but she counted wrong. I mean, she counted it, so everything's good now. So we can move on. Okay. So clear everything and move on. Okay. All right. Let's complete the sample space below for the situation of tossing 2 fair dice. Now, if we do this incorrectly, like someone mentioned earlier, there's 6 outcomes for the first die. There are 6 outcomes for the second die. So we might accidentally say that there's a total of 12 outcomes, but there's not. There are 36 outcomes. 1 on the first, 1 on the second, 1 on the first, 2 on the second. What will be the next one?
1 and 1, 3.
1 on the first, 3 on the second, 1 on the first, 4 on the second, and so on, right? All the way down to 6 on the first, 6 on the second. It might take me like 8 hours to fill this out. But I'll start as we start answering the questions on the right. So first, are the 36 outcomes equally likely? Yes or no? Assuming fair dice, are each of these 36 outcomes equally likely? Someone chat.
Yes.
Say. The answer is yes, that is correct. So now that we know that they're equally likely, what is the probability of rolling doubles? In other words, out of these 36 outcomes, how many of them are doubles?
6 of them.
6 of them, right? You have 1 and 1, 2 and 2. I didn't get there, but 3 and 3, 4 and 4, 5 and 5, 6 and 6. So 6 possible ways of getting doubles, 36 total outcomes, equally likely. So the probability of rolling doubles would be 1 in 6. It should happen 1 every 6 times. So if you're playing Monopoly or some game where doubles get you a reward, it should occur 1 out of every 6 times. Maybe backgammon. Anyone here play backgammon? Sheshpesh? No? So if you roll doubles, right? Very, very, right? I think it's a good thing. I haven't played in a long time, but you get another roll, right? I think. So yeah, doubles are good. Anyways, next, find the probability of rolling a sum of a 7 or an 11. Now, this is not 2 questions. It's 1 question. You're perfectly happy with either a 7 or an 11. So you want to find the total ways of getting a 7 or 11. How many ways are there of getting a 7 or 11? Now, if I filled out the table, it'll be easier to read and see, but I didn't because I got bored. But try to analyze of what's coming and come up with a guess for the probability of rolling a 7 or 11. And for bonus points, which game might you be playing where rolling a 7 or an 11 is a good thing?
6, so 1 of 6 to get a 7.
Say that again, I'm sorry.
You can get a total of 7, and the probability would be 1 out of 6.
Right, but we don't want just sum of 7 by itself. We want a 7 or an 11.
Or an 11.
Right, we're happy.
2 out of 36 chance of getting an 11 because only 5 and 6 add up to that. And we can have 5, 6 and 6, 5.
Okay, so what's the answer to the question then? Because I got this by itself, someone gave me that, which is great. I got this by itself, someone gave me that, but that wasn't the question. The question was either one. We're looking for the probability of either one.
Be an 8 out of 36.
So 8 out of 36. Because there's 6 ways of getting this, 2 ways of getting this. So out of the 36 outcomes, we are perfectly happy with 8 of them. 36 equally likely outcomes, 8 out of 36, that's 4 out of 18. That is 2 out of 9, which is 22% approximately. So anyone for bonus points know what game a 7 and 11 plays a central role? Nobody went to Vegas? Come on, you guys should know this. You guys are all adults. I'm confused. Well, that's not the answer, but what are you confused about?
I'm confused on the how does it sum up to 7, or how do you sum up to 11?
Well, would you agree? I'll switch colors here, but would you agree that if I roll a 5 and a 6, I just rolled an 11?
Yeah.
How about a 6 and a 5?
Yes.
Okay, how about a 1 and a 6?
7,
How about a 2 and a 5?
7.
How about a 3 and a 4, a 4 and a 3, a 5 and a 2, or a 6 and a 1?
Okay, so 7. So you're basically adding both rolls.
Well, that's how rolls work when you roll 2 dice, right? When you roll 2 dice, it's the sum of the 2 that you care about in most games. I know sometimes I forget that not everyone grew up in my generation where board games were your usual Saturday afternoon activity, so, or just Monopoly, Risk, all the different games. But in most board games, you roll 2 dice, it's the sum of the 2 dice that matters. Does that make sense?
Yeah.
Okay.
Professor, do you mind scrolling down a little bit? For me, it cut off. Like I can't see the bottom.
With my writing or the
Your writing, yeah, I know with your writing.
unfortunately the writing won't scroll with the rest of the work.
Okay, so you put 8 over what?
8 over 36
Equals what?
equals, well, just reduce 4/8. equals
Oh, okay
3
then.
divided.
Okay, then I got it. Thank you.
Okay. So I'm gonna go ahead. Hopefully I can erase this all. You're okay with it? Yes, no?
Yeah.
Okay. So now it says construct a probability distribution table for the sum of two dice. Wow, okay, I know I'm boring, but you don't gotta yawn that loudly. Okay, so construct a probability distribution table. Yeah, that's you, that's right. I saw that. Construct a probability distribution table for the sum of two dice. So we care about the sum. What are the possible values that the sum could take when you roll two dice, each one, individually from 1 to 6? What are all the possible values that you might get when you add them? What is the smallest possibility you might get when you add two dice?
2.
2, right? You can't get a 1 because each one is going to be at least a 1. And can you get a 3 when you roll two dice?
Yes.
How about a 4? All the way, what's the highest number you might get when you roll two dice?
12.
12. Okay, now, of course, you shouldn't leave this blank. It's very hard for me to write with this thing, but 5, 6, 7, 8, 9, 10, 11, 12. So the question is, now that we have all the possible outcomes, all the numerical outcomes, what is the probability of rolling a 2? Out of all of those 36 outcomes in the previous page, how many of them would result in a sum of a 2 when you rolled two dice?
Only one of them.
Only one of them. Someone
1 out
chatted
of
that was the
36.
answer one, so the answer 1 out of 36. Okay, so the probability of rolling a 2 is 1 out of 36, which means it doesn't happen that often. And in your experience of rolling dice, if you've ever played these games, how often do you roll a double 1? Snake eyes. How often do you roll it? Not often. Not often. It's kind of rare. How rare? Well, 1 in 36. That's exactly the point. Now, what about rolling a 3? What is the probability of rolling a 3?
2.
Just 2, straight up 2?
2 out of 36.
2 out of 36. And how about rolling a 4?
3 out of 36.
3 out of 36. And go ahead, even though I'm not writing them, but go ahead and fill out 5, 6, 7, 8, 9, 10, 11, 12. So that you can answer the question that's just beneath, which is what is the most likely sum? Also, by the way, you should notice something, a pattern that might help you. When you look at this square grid, which squares correspond to a sum of 2? Or which square, since there's only one? Which square corresponds to a sum of 2?
The first one.
The first one, right? Which square or squares corresponds to a sum of 3?
The second one.
I'm sorry?
The second one and the one down.
So these two.
Yeah.
How about a corresponding to a sum of 3? Sorry, I meant 4. Corresponding to a sum of 4.
The 3 diagonal.
Sorry?
The same 3 down diagonal.
So do you see a pattern for the number of squares corresponding to a given answer, to a given number?
Yes.
Yes, right? So we should see it. So we can use the pattern to get these answers. 1 out of 36, 2 out of 36, 3 out of 36. What's next? For 5.
4 out of 36.
4 out of 36. What's next? For 6.
5 out of 36.
5 out of 36, 6 out of 36, back to 5 out of 36, 4 out of 36, 3 out of 36, 2 out of 36, 1 out of 36. And hopefully they all add to 1. Oh, no, I don't want to do that. Hopefully they all add to 1. Spoiler alert, they do. Does that make sense? This is where you say yes.
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 Oh, okay, great. Good, good, excellent. Now, so what is the most likely sum when you roll 2 dice? What sum is going to occur more often than all the rest?
6.
Try again.
6/36.
Well, 6/36 is the likelihood, but we're looking for the actual most likely sum, not how likely it is to happen, but what is the most likely sum?
7.
7, actually,
7.
because it's 4/36, 5/36, and 7 is 6/36. It's more likely to get a 7 than it is to get anything else. Do we agree?
Yes.
Okay.
Yeah.
Now let's play a
Yes.
different. Hey, that's what I'm talking about. A belated yes. Okay, try to be a little earlier next time, but otherwise that was amazing. Now, we're going to play a different game here. Okay, this game that we're going to play now is not let's add the two dice together, but rather let's use the larger number. And of course, if they're the same, then that number. So let's make a probability distribution table for this new game where I don't care about the sum, I care about the larger number of the two dice. So what are the possible numerical outcomes for this game?
1 through 6.
1 through 6. The larger number of two dice that are each 1 through 6 can never be more than 6. Agreed?
Yeah.
Okay, now, what is the probability that the larger of the two numbers is 1? How many of those 36 equally likely outcomes is going to have the larger number being 1?
1.
1 out of 30.
1,
But
right? The only way to get a 1 is if both dice are themselves 1. Do you agree?
yes.
Okay, well, what's the likelihood now? I'll move it to the side so there's a little more room, but what's the likelihood now that the larger number is 2?
2.
2 out of 36.
Try again.
3.
So what is it?
3.
Just 3 straight up?
3 out of 36.
3 out of 36. Can you explain why, or is that just a guess?
That was a guess.
Okay, well, it might be wrong, it might be right, but I don't want to give it away.
Wouldn't it be 4 out of 36?
If it's 4, tell me what those 4 are. What are those 4 outcomes where the larger number would be a 2?
A 2.
Sorry?
Oh no, I thought we were on 3.
3, 4, 5, 6.
Well, hold on. You rolled 2 dice. Give me a possible way of rolling 2 dice where the larger number is 2.
You could
1,
have 1, 2,
1, 2, and 2.
1, and
2,
2,
1, and 2, 2. Yeah.
Okay, you can have 1 and 2. You can have 2 and 1. And you can have 2 and 2. Are there any other ways that the larger number could be a 2?
No.
'Cause I heard someone say 4 earlier.
Would 1 and 1 count?
Well, the larger number for 1 and 1 will be 1. Right? If it's 1 and 1, the larger number is 1. That's where this one came from.
Mm-hmm.
Right? For 2, there's only 3 ways of the larger number being a 2. How many ways can the larger number be a 3?
5,
Excellent. What are the 5?
1, 3, 3, 1, 2, 3, 3, 2, and 3, 3.
Fantastic. If we actually go back to here, to the square, can you give me a nice little pattern like we had for the last problem for how many will have the larger number 1 and how many will have the larger number 2 and so on? Let's cross them off. Which one will have the larger number of 1?
1 and 1.
1 and 1. Which ones will have the larger number of 2?
1, 2, 2, 2, and 2, 1.
Which ones will have the larger number of 3?
1, 3, 2, 3, 3, 3, 3, 2, and 3, 1.
Do we see a pattern yet?
Yes.
That's what math is about, by the way, pattern recognition. So how many ways is the larger number going to be a 4? Or more specifically, what's the probability that the larger number is a 4?
7.
7
Seven.
out of 36.
36.
7 out of 36. And how about, so someone texted, yeah, okay, good. And how about the larger number being a 5?
9.
Sorry,
9.
9, just straight up 9?
9 out of 36.
9 out of 36. And what's the probability the larger number is going to be a 6?
11 out of 36.
11 out of 36. So rather than doing things one at a time with no association to the one that came before it, if you look for patterns, quite often things become a lot clearer and save you a lot of time. Of course, spending the time to find the pattern is not always necessarily the easiest, but once you find it, it does make things very, very straightforward. So in this case, what is the least likely larger number?
1.
1. Right, 1, exactly. All right, so what is this nonsense? This lessons, oh, what is this crap? Oh, so this is just like, things that 7th graders need to know, but this is not actually teaching you anything. Okay, well, that was fun. Any questions on chapter number 1? Unit 1. All right, well, we finished unit 1 today on Thursday, and we know what that means. Do we all know what that means? I hope we all know what that means. Do we all know what that means? I know what that means. Do you guys know what that means?
Homework?
Hi, look at you, homework. Yes, the homework is due a week from today. Now, I'm not going to be checking the homework, but we'll have a quiz on it. And again, I like to base quizzes on homeworks. So if you do the homeworks, then you might have a good chance of doing well on the quiz. So when should we have the quiz? That's a great question. Do we want to have the quiz on the day that the homework is due? No, how about this? The homework is due on Thursday. I'll answer whatever questions we have on that homework. And then the quiz you'll do that weekend out of class. It's got to be done between sunset Friday and sunset Saturday, no exceptions. I'm kidding. Oh yeah, that was a joke for you and you alone, but nobody else got it. Okay, good. So anyways, it's a whole Jewish thing, guys. Don't mind us. We're weird. All right. So anyway, I'll give you the weekend to do it, and it'll be due by Tuesday, by the time we come back. So the first homework and first quiz will be next weekend. But let's move on now to the second chapter. So, and before we do, I actually want to update the syllabus because I came up with my office hours. So I am going to share the screen as I change my syllabus so you guys can all see this. So let's edit this. These office hours are going to be Tuesday from 12:55 to 2 o'clock. That's just before our class. 3:15 to 4 o'clock. That is just after our class. And 5:40 to 6:30, which is way after our class. And Thursday, just 5:40 to 6:30. You might say that's some weird hours you got going there, and it's true. It is some weird hours. Basically, I have to fit in a certain amount of hours exactly, and I have to put in 3.5 hours per week, and this gives me exactly 3.5 hours. But because of my other teaching schedules, it's kind of hard to find time. So this is like the perfect times that just barely fit in into all my little blocks and everything's perfect. If you cannot make these office hours and you really, really, really need to meet with me, just send me an email and we'll try to find something that works for both of us. Sound good? So now it's up there on syllabus and you can look at it at your leisure. Okay, so chapter 2, since there's no questions on chapter 1, let's move forward. Simulation. Oh yeah. What is a simulation? I'm glad you asked. It's a great question. So if I asked you to roll a coin 1,000,000 times, you'd probably tell me not to, or that you're not going to, with some very strongly worded words that I can't say in public. So what we do instead, we generate a simulation which has the same overall effect as flipping a coin or whatever our experiment is without actually doing it. So you ever have to flip a coin and you didn't have one handy? So you just take a leaf instead, and you say this side is heads and this side is tails, and you flip the leaf instead. You're simulating flipping a coin by using something else. Now, of course, that's a silly example because it's basically the same thing. So we're going to do a whole chapter of more sophisticated simulations. Okay, so first, what is a simulation? It's a method of estimating a probability empirically, that means using data, by using a device that generates outcomes with the same probabilities as the actual situation. And usually, especially in elementary school, what are the devices that we use to simulate? Spinners, dice, cards, coins. Okay, and so here we have a deck of cards. There are 52 cards in a deck, 4 suits of 13 denominations, ace through king. I know it seems obvious, but not everyone knows that. So, according to the High School Youth Risk Behavior Study, 1/3 of Los Angeles Unified School District high school students reports that they have tried cigarette smoking. 1/3. How can you model the situation of picking 12 high school students at random and counting the number who have tried cigarette smoking? In other words, one thing I can do is I can go to one of these schools and pick 12 students at random and say, you, and so on. Have you smoked? Have you smoked? Have you smoked? Have you smoked? And I'll get maybe 5 of them, 6 of them, 3 of them, 2 of them, whatever, who'll say, yes, I've smoked. And I'll have this data that represents how many in 12 smoke. But if it's really true that 1/3 of them smoke, I don't actually need to pick them. How can I use cards to model the same scenario? So can anyone take a guess as to how I can use cards to model the same scenario? Oh, someone chatted. Maybe they have the answer. They said, saying different suits smoke. Can you be a little more specific there?
I think they mean by the colors, right? They could.
I don't know. That's why I'm asking.
I think that's what the person maybe means.
Maybe, but I'm looking for much more precision of the answer. I mean, it could be right. I'm not saying it's right or wrong. I was going to say like hearts and spades and diamonds smoke. So if hearts and spades and diamonds smoke, I guess that means that clubs do not smoke, right? Okay, that means 3 out of 4 smoke. Correct? That's what you're saying? Okay, but what are they telling us is the proportion of those who smoke? According to their study.
1/3.
1/3. So your guess, and it's great that you guessed. I love it. It's not correct, but I love that you guessed. You came up with a scenario where you got a 3 out of 4 chance of smoking, but the actual chance of smoking should be 1 out of 3. So we need a scenario where it's 1 out of 3, not 3 out of 4. So I'll give you this one because I'm nice. I'm not really nice. Don't tell anyone, but I'll pretend to be nice. I'm going to take 3 cards, an ace, a 2, and a 3, and I'm going to shuffle them, and I'll pick one at random. I will say that the ace represents smoking, and the 2 and the 3 represent non-smoking. If I pick an ace, that means that the student that I just questioned said what when it comes to smoking or non-smoking? Do they smoke or do they not smoke?
They
They
smoke.
smoke.
They smoke. If I pick a 2 or a 3, does that mean they smoke or they not smoke?
No, they don't.
They don't smoke, correct? So do you agree that I was able to create a scenario where there's the same likelihood of occurrence as the actual scenario, where I didn't have to actually go out and do anything with real people? Because I hate people. I don't like talking to people. Plus, people lie and stuff. I don't want to go there. Plus, I have to go to a US, what is it called? The United LAUSD. Do I really want to go to an LAUSD school? No, I don't want to do that. Don't even like Cal State. So what I'm going to do is I'm going to simulate. I'm going to create a scenario where the probability is the same as the actual scenario, but uses a much simpler device to get the answer. So I'll shuffle, pick a card, shuffle, pick a card, shuffle, pick a card. And I'll do this 12 times. Every time I pick a card, it's like asking one student, do you smoke? The total number of aces is the total number of kids who said, yes, I smoke. The total number of 2s and 3s, the total number who say, nope, sorry, I don't smoke. Does that make sense? Yes, no, have I lost anyone?
Yes.
Yeah, you kind of lost me. So each time that you would do that, you would only pick 3 cards.
No, I would always have 3 cards.
Okay.
Each time I pick is the representation of asking a student, do you smoke? If I pick the ace, the student just said yes. If I pick a 2 or a 3, the student just said no. Reshuffle, go on to the next student, pick a card. Ace, they say yes. 2 or 3, they say no. Reshuffle, pick another card, that's the next student. I do this 12 times. Every pick is asking the student, do you smoke? Every ace is the student saying yes. Every 2 or 3 is the student saying no.
Gotcha. Thank you.
Does that make sense?
Since you're doing that and there's a sample size of 12, each card would count for 4 students.
No, I do this 12 times. But each pick is a different student.
Oh, I see.
So 3 cards, pick, reshuffle, 3 cards, pick, reshuffle, 3 cards, pick. Every pick is one student. I pick 12 cards, but each time I pick, it's always a 1 in 3 chance. Because the actual situation is always a 1 in 3 chance. So I have to have my model represent reality.
Can you also model it by making all face cards, like just separating all face cards and making a single suit representative of kids who smoke?
If you separated this face cards, so you have 12 face cards, correct?
Yeah, and then I say that all hearts represent smokers, and then I draw 3 cards.
Well, if you represent all hearts, first of all, that's 1 in 4, is it not?
It is, okay, yeah.
Well, it's okay. So let's say I remove the spades. So now I have 9 cards, 3 of them are hearts. So it's a 1 in 3 chance.
Yeah.
But I don't pick 3 cards because every time I pick a card, now it's no longer one out of 3.
Yes.
Now it's going to be something out of something else.
Mhm.
You have to recreate a 1 in 3 situation every time. So if I'm going to use 12 cards or 9 cards, why not just use 3 cards? Isn't it a lot easier?
Yeah, it makes sense.
Yeah. Okay. So let's do another situation. What if I didn't want to have cards at hands? What if instead I had a spinner? How can I model the situation with a spinner instead?
Could you divide the spinner into 3 parts and then like make one specific part for smoking, non-smoking, non-smoking?
Beautiful. Divide the spinner into 3 equal parts. Say something like, you know, from here to here, and then here, smoking, non-smoking. So I've created a scenario where there's a 1 in 3 chance of landing on smoking. And then how many times do I flick the spinner?
The 12 times.
12 times. Every flick of a spinner is asking a kid, hey, do you smoke or do you not smoke? Make sense?
Yes.
Could I use dice to represent this model? Could I simulate with dice? Or a die? I don't necessarily need more than one, but if I had dice at my disposal, could I use those instead?
Yeah, wouldn't it be 2 dice?
Well, okay. I mean, I would use one die, but if you want to use 2, you can. What would your 2 dice be? You there? 2 dice works too. What would you, how would you model it?
Smokers and non-smokers.
I'm sorry, say it again.
Smokers and non-smokers.
Right, but what outcomes model smoking and what outcomes model non-smoking?
Mm,
You need a scenario where there's a 1 in 3 chance of getting smoking and a 2 in 3 chance of getting non-smoking.
Can it be odd and even numbers?
For 2 dice or for 1 die?
Okay, let's do 1.
Okay, so if you do 1 die,
Mhm.
then odd and even is, what is that? That's not a die. Hold on a second. It's supposed to be,
That was completely not a die.
supposed to be a die. So if you do, okay, it's supposed to be pixels, but let's say it's 1, 2, 3, and 4, 5, and 6 are in the back. Okay, so if you do dice, odd and even, that means there should be a 50% chance of one outcome and 50% chance of the other, correct?
Mhm.
But we want a 1 in 3 and 2 in 3.
No, okay.
But I can still use a die, I just have to adjust what you said. So what would I call smoking and what would I call non-smoking? If I want to use a die.
You would assign specific numbers. to
Okay, so give me an example. What can I assign for smoking and non-smoking?
So like how she said, like 1, 3 could be smoking, and then 2, 4 could be non-smoking,
And how about 5 and 6?
non-smoking as well.
Okay, so I might have picked 2 numbers in succession, like 1 and 2, but it's okay. As long as you've created a scenario where 1/3 of the time you're going to land on smoking versus non-smoking, it's a perfectly okay simulation scenario. Does that make sense? Yes?
Yeah.
Okay.
Yeah, that makes sense. Yeah.
Okay, could you use coins to simulate it?
We're not there because then it's 50-50.
Right, well, certainly not 1 coin, and even 2 coins. I don't know how I would create a 1 in 3 chance with 2 coins. I would not use coins in this scenario. I can't really think of a scenario. Well, actually I could. No, I can't. No, actually I could.
Unless you put like unless you do 3 coins on one of them, you put a sticker over it and then you leave it blank. Wouldn't it be on that?
Well, but even if you did that, it still is 2-sided, so it's still 50-50. But you can do
Yeah,
this.
that's true. Yeah.
But you can do this. I don't necessarily recommend this, but it works. I can say heads is going to represent smoking. Heads tails and tails heads represents non-smoking. And I'll say that tails represents a do-over. So in that case, there's a 1 in 3 chance of getting each of the first 3 outcomes because essentially tails you're removing as a possibility. But that's a little convoluted.
Can you just make it 2 heads is smoking, 1 heads is non-smoking,
No,
and
because
0 tails?
No, because remember, 2 heads was a 1 in 4 possibility. Just because 3 outcomes doesn't mean they're equally likely. Remember that?
Yeah.
Right, it's okay. Getting things wrong is part of learning. I actually prefer wrong answers that I get to make fun of than no answers that I get to just think and make fun of in my head. So I always prefer that. Anyways, any questions on this particular scenario? Okay, we did it with a die already. We did it with a card already. Oh, look at that, I'm ahead. Okay, so here's another one. About half of all kindergartners are girls and half are boys. So let's assume that it's a 50-50. across the United America states and world and whatnot, and any other planets that might have alien children. So you are assigned to a class of 15 kindergartners that has 5 girls and 10 boys. So you wonder whether having so many boys can reasonably be attributed simply to chance because, hey, anything can happen, or whether you should look into the reason. Okay, so unlikely outcomes can still occur. If I flip a coin 10 times in a row, can I get 10 heads in a row even if the coin is fair? Is that a possibility? Is anyone with me?
Yeah.
Whoa.
Yes. Yes, we're here.
Okay. So if I flip a coin 10 times in a row and I get 10 heads, is it possible for that to happen when the coin is fair?
Yes.
Yes. Is it likely for that to happen when the coin is fair?
No.
No. In fact, it's pretty rare. It's 1 in 1,000. Technically 1 in 1,024, but let's say 1 in 1,000. So if I got 10 heads in a row, what might I start suspecting?
Is it fair?
Yeah, I might start suspecting, hey, maybe the coin wasn't fair to begin with. Maybe my belief as to the likelihood of each possible outcome was wrong. So in this example, I have a belief that there's a 50-50 chance of whether a child is a boy or a girl. And therefore, if I have 15 kindergartners, I would expect to have 8 and 7. That's what I would expect to have. Is 5 and 10 so far off the mark that I would start to question whether my belief was incorrect, or maybe something is really weird in this community or this class or this school, or maybe there's something going on behind the scenes? I don't know. We'll get to this later in the course, attributing numerical likelihoods to different outcomes as to whether or not it's reasonable to think it might occur. However, the point here is we are going to model a kindergarten class by flipping a coin. Is that a good simulation for modeling the number of girls and boys in my kindergarten class? Would that be a good simulation?
Yes.
Yes, 50-50. What would the simulation be? If it's a heads, what would that be equal to?
Maybe girl.
Okay, so let's say heads means that that child is the girl, and tails would mean that that child was a boy. And I might run this simulation. How many times would I flip this coin?
15.
15 times. Every child is a flip. Now, if every one of us did this, there's what, 30, 40 people here, give or take? So if every one of us did this, and I got 5 girls, 10 boys, let's say 1 out of 40 times, let's say it only occurred once, I might start to question how likely it is that my assumption is correct of half and half. Because 1 in 40 is not exactly the most likely outcome. But if I got 10 in 40, which is 25% chance, if something has a 25% chance and it occurs, will you start questioning your existence and everything you know about the world? No, 25% chance, 1 in 4. It's not the most likely outcome, but it's certainly reasonable, right? Yes? No? Am I making sense?
Yes.
I hope so. Okay, so the idea here is that if you run a simulation multiple times and you never get a certain outcome, no matter how many times you do it, or you get it really, really rarely, you might start questioning your underlying beliefs. Where if you get it a certain percentage of the time, 10%, 20% more, it's fairly reasonable. Of course, we're not in a class right now. If I was in an actual class, I might perform this experiment where each of us flips a coin 15 times and counts the number of boys. by the way, in terms of a probability distribution, what are the possible outcomes for the number of boys in a class of 15 students? Not everyone at once now. What are the what are the possible outcomes of how many boys there are in a class of 15 students?
Wouldn't it usually be lower?
Well, I'm just asking what the possible outcomes are.
They could be all boys.
It could be all boys, which is 15 boys. That's a possibility. What else?
Um,
And then one.
One
And you
boy,
decrease,
two
like-
boys.
One boy, two boys. I mean, no boys, which is 0. Right? These here are all the possible number of boys that you might have in a class of 15, correct?
Yes.
So if I ran this simulation with a coin, I'd probably expect to get numbers near the center quite more often than numbers near the edges. Right? 7 boys, 8 boys, I'd more likely get these numbers lots of times than no boys or 15. In fact, I might not even ever have 0 boys in a class of 15. If we all did this, what's the likelihood that every one of your flips is a heads? And you get no boys whatsoever? Very unlikely, correct? It might never happen.
Mhm.
But here we would expect lots of them. So the question is, if I end up with 10 boys, what's the likelihood of this outcome?
5.
Well, I don't know. I didn't do it. I'd have to run the simulation. I'm just saying that that would be a question that I might ask. Does that make sense what I'm saying so far?
Yeah.
So the purpose behind simulations, it seems reasonable.
Mhm.
So suppose someone went ahead and actually did the simulation. They actually did it. They did 1,000 runs. They did it 1,000 times. Are the outcomes here of how many boys I had each time, do those seem fairly reasonable and what you would expect? Does it seem, what is that noise? Does this seem fairly likely as an outcome for 1,000 simulations? That 206 times I got 7 boys, 207 times I got 8 boys, and so on.
Yeah.
Yes.
Yeah, it's reasonable.
Yeah, lots of times near 7 and 8, even 6 and 9, lots of times, even 5 and 10. How often did I have 10 boys? 78 times out of 1,000. What percentage is that? How often did I have 10 boys in my simulation if I had 78 out of 1,000? What percent is 78 out of 1,000? That is not 80%. 80% is a lot. 78 out of 1,000 is not a lot.
Like 40.
No.
7.8%.
7.8%. It's less than 10%. I mean, 10% of 1,000 is 100. It's less than 10%. It's about 8% of the time. Now, if something happens that had an 8% chance of happening, would you start to question everything you know about the world? Or would you say, unlikely, but certainly possible? What would your outcome be in that situation?
I think Emily Heckman, has a speaker on, like we can,
There's
She's
a lot of
on-
background noise.
Emily,
sorry about that.
I forgive you. So if something occurred that only occurs 8% of the time, is that a low enough chance of occurring that you start to question everything you believe if it happens? Or would you say, I didn't expect it, but okay,
But it's possible, yeah.
it's certainly
It's
possible.
questioning, I mean, you'll be like, wait, what? You know, because it only happens 8% of the time. It's pretty
Right.
low.
It's pretty low, but is it
Yeah.
but is it so low that you'd be like, what? How did that happen?
Yeah.
So that's the question. How low is 8%?
I mean, out of 100, it's really low.
Sure, it's low, but let me see this question. If I offer you $1 million for doing something that had a 1 in a million chance of your death.
Oh no, then it's pretty high. It's high. No.
Okay.
No, when you put it like that, like no, it's high.
Okay, so 8% is
It's
high
like when
enough.
someone talks to you, like you always ask them, okay, what percent chance do I have? You know,
Right.
give me let's
Right.
talk numbers now.
Yes,
know?
exactly. Yeah. You go to the doctor and they're like, yeah, you want this procedure, but 8% of people who have it, are paralyzed.
Exactly.
You say
you always ask the doctors, what's the percentage of me coming out alive, me coming out of this? Yeah, you always ask.
Right, exactly. So if they said 8%, you'd be like, I pass.
It's high. When
Right,
you
but
ask like that, it's high. It's a high.
Right. But if they say it's 1 in a million, then you might start to think, okay.
When you put it like that, yeah.
Yeah, okay. So that's the idea here. Something, and by the way, just so you know, in mathematics, this is a very big thing where you assign a cutoff for which you say less than this, too rare, more than this, I'm not questioning it. And we're going to do that later in the course.
Okay.
So in your minds, what you're telling me in your mind is that 8% is high enough that, okay, I'm not questioning it.
I think for us also, we see it as like a low number. I think it has to do a lot with our grades, we see it as we see it like that. I think that's why we're like, oh, it's a low number. It's low because we always see the cutoff after 50. Yeah, that's why. But when you put it like how you were saying it, like one of them, I'm like, okay, then that makes a huge difference. Yeah, when you put it like that, it completely changes.
Excellent. So good. So seeing things from multiple perspectives is always a good thing.
Yeah.
Okay, so what do the numbers on the lower axis represent? These obviously represent the possible outcomes, right? 0 to 15 boys, those are the possible outcomes in this scenario. What on the vertical axis? Those are the frequencies, how often they occurred. With these numbers, of course, here being the actual frequencies, right? This is how often each one actually occurred. So what is the probability approximately of getting exactly 4 boys? As a fraction, we'll keep it simple. What's the probability of getting exactly 4 boys? Based upon this table here.
51 out of 1,000.
51 out of 1,000. How about 4 boys or fewer?
You add the other numbers, right?
Sure. 51, 11, 5, 2, 62, 69 out of 1,000. Right? Both pretty small numbers, but still possible. Okay. So if I were to make a probability distribution here, I would list all of the outcomes 0 to 15. And then for 0, it will be 0 over 1,000. For 1, 2 over 1,000. For 2, 5 over 1,000, and so on. I can fill that out if I was so inclined. And those would, of course, add to 100% because these numbers have to add to 1,000, and 1,000 over 1,000 is 1. Do we agree with that? Seems fairly reasonable. So the question was, back to the original question, what's the likelihood that a kindergarten class would contain 10 or even more boys? 10 or more. 10, 78, 88, 98, 103, 121, 126, 127. 127 over 1,000 would be the likelihood of getting 10 or more boys, approximately, which is what, 12.7%, correct? Right?
Yeah.
High enough that if it happens, I don't start to question and say, wait, what's going on here? Okay, it might not be the most likely outcome, but it happened. It's not the most shocking either. Okay, so can being assigned to a class of 15 that contains 10 boys and 5 girls reasonably be attributed to chance or loan? Or are you justified in questioning how this happens? Because we got 12.7%, that's high enough that it's going to happen now and again. I'm not going to question how it occurred. It's just going to say, wow, that was rare, and just go on with my life. Whereas if it was like 1%, I might say, wait, what's going on here? This doesn't make sense. Does that seem reasonable?
Yes.
Yeah.
Okay, we are going to stop here. In general, on Thursdays, as you can see, I'm still in my high school. I teach until 2, and then I teach at 3:10. So I fit you guys in right in between 2 high school classes. It's tight. In general, I'll always be here on time, but I will have to leave on Tuesdays and Thursdays 5 minutes early. So we're going to end here, and we'll start here next time on page 9. So somebody remember, because I'm going to forget. And yeah, are there any questions? I'm going to stop sharing. And I'm going to stop recording.